Well, hello and welcome to this session. Can you raise your hand if you have a seat near you so that the people that are coming can get a seat? Okay. There are still seats in the middle if you want to have a seat. Prefer to sit while listening to the concurrent and asynchronous programming state of Loom. Now, the Loom project has been around for many years now. And guess what? We will have a portion of the Loom project. There are 3 parts in the Loom project. The first part will be delivered as a final feature, should be delivered as a final feature in a JDK 21, as we are going to see. So virtual threads are actually not that virtual because they are a reality. But they are still virtual. But they are still a reality. I should really have I've called this talk Concurrent and the End of Asynchronous Programming with Loom, because Loom is about that. It's about replacing this asynchronous programming model with something else that is simpler, easier to read, to write, more performant, and easier to maintain in the long run. And this is what I'm going to, well, I will actually try to show you that. Okay, my name is Jose. I work at ThreadLocal. Here's a bunch of links with content I publish on the internet. If you check my YouTube channel, you will see quite a lot of content about Loom, concurrent, structured concurrency and this kind of thing. We have only 50 minutes, so I'm going to condense everything and focus mostly on virtual threads and give you a hint about the rest. Here is a link to the dev.java website, which is the website we're holding the up-to-date documentation of the JDK. It's held by the Java Platform Group and by the DevRel team. I'm part of it. I wrote quite some content for the dev.java website. Don't try to print it, because under the Learn tab you have something like 1,000 pages of content. So you can read it, but don't print it. It will be bad for forests. And here is the set of well, not all the content, most of the content we publish with the DevRel team at the Java Platform Group at ThreadLocal. Most of it is on YouTube, but you also have audio content with podcasts. Personally, I love podcasts. This is my preferred content, and also written content on the dev.java website. And if you're in podcast as I am, you can check the inside.java/podcast, and you have several episodes of them that are talking about Loom very precisely. And the last one, Elidon Nima on Virtual Thread with Thomas Langer, who is one of the main developers of the Elidon project, is really interesting when it comes to replacing precisely non-blocking asynchronous programming with blocking code built on virtual threads. It's super interesting. That being said, Loom is still a work in progress. I would say less and less, because a fair amount of work has already been done, especially virtual threads that have been integrated in the JDK 21 branch already. So technically speaking, there is a process to remove them if something goes really, really, really very wrong, but it shouldn't happen. And we should have them, you should have them as a final feature in a JDK 21. Now, JDK 21 is due to be released in September. That's literally tomorrow. And the first early access versions should be available sometimes in June or July. So that's also very soon. Anyone already running on Java 17? Oh, that's most of you. I would say probably more than half of you. So moving to 21 should be easy once you're already on 17. Anyone still on 8 or 8? Yeah, Java 8? Come on, guys. Earlier than 8? Oh, no. All right, we need to do something for you. Java 8 is almost 10 years old now. You know that? Yeah, okay. Just saying. Just to give you an idea about the amount of work of the project Loom, that's a tweet that my friend David Delabase did a while ago, something like last year, when the first virtual preview version of Loom was made available in the JDK. And that's the pull request of the Loom project on the JDK branch. So everybody knows what a pull request is, right? You're doing pull requests every day, or at least every week, okay? 100,000 lines. Does that talk to you? That's a big pull request, right? Okay. Anyone already made code reviews? You're doing code reviews, right? 100,000 lines for code review? Does that talk to you also? So that's the first part, virtual thread. should be final feature in the JDK 21. The second part, and we are going to cover that really quick at the end of this presentation, is structured concurrency. And that the second incubator in the JDK 20, so you can actually already play with it. It has not been integrated yet in the JDK 21. It should be. And it should be integrated as a preview feature instead of an incubator feature. Now, the difference between both is a little slim from the concept point of view. There is one big difference, is that the package for incubator feature is jdk.incubator.something, and in that case, it's concurrent. Whereas the package for preview feature is the final package name. So Java util, probably concurrent something. Okay, so that's the biggest difference. And the third and last part of Loom is ScopedValues. And the ScopedValues should also become a preview feature in the JDK 21. It hasn't been done yet, but it should be done in the next few weeks. Okay, if you want to learn more about Loom, provide feedback, you have one link to remember, which is this one, jdkjava.net/loom. This is where everything is happening. You know that in the OpenJDK Association, everything is happening in the open. All the mailing lists are open. You can just read the archive, and you can subscribe to them if you wish to post feedback or report bugs on them. Okay, and that's the link you want to follow if you want to have that. If you want to play with early access versions, if you want to play with features that are not in the JDK branch yet, this is also where you want to come. Loom is already something that is well, many people have been talking about it. This is a set of articles that are talking about it from outside the OpenJDK itself. Okay, so you can see that most of the main frameworks that you're probably using are already either embracing Loom or Inverter Threads, or at least evaluating, in the process of evaluating what Loom can bring to these frameworks. And the results are really very good so far. That's the reason why Loom will make it as a final feature. You have everything there. You have Quarkus, you have Tomcat, Elidon, Spring Boot, Vertex, of course, Jetty. Which one is this one? Yes, that's Spring Boot. So, yeah. I would like to put things in a perspective, in a historical perspective. Maybe some of you remember the days of Java 1. Java version 1, not the conference. Yeah. So Java was actually, right from the beginning, one of the only language that had a concurrent programming model baked in a language from the very first versions. Okay. The first really usable version was probably Java 2 in 1998. And in 1998, you had the thread class, synchronized keyword, a model for your task, which was runnable, this interface, runnable. Everything was there so that you can do concurrent programming. Now, of course, in the 90s, concurrent programming had nothing to do with what it is now. It mostly changed in mid-2000 when multi-core processors became a thing and became common. Now we all have multi-core processors, but back in this time it was not the case. And in 2004, that is 10 years after that, we had this new Java util concurrent API that was added to the JDK. So it's not a language change, it's just an API change, but it's already a massive change, because this Java util concurrent is actually bringing several new concepts. The first one is the concept of executor service. You should not be creating threads by hand anymore, starting with Java util concurrent. That's Java 5, okay, 2004, sorry. And the second concept it brings is a new model for your task, which is callable. And now callable can return a result, and it can also throw exceptions, whereas a runnable task is completely silent. It doesn't throw any exception, cannot throw any exception, and it doesn't return any value. Okay? But because you need to talk to your tasks, because when you submit your task on executor service, you need to get back the result in the thread that actually submitted this task. You need also a future object. So the concept of future object was needed for this model of tasks. And through this future object, you can actually interact with this task. You can get the result, get the exception if it threw an exception, and you can also cancel it or set a timeout for the execution of this task. That was the revolution of Java util concurrent. Now, this executor service is actually a pool of thread, and we are going to talk more about thread pools in a minute, so that's why I would like to focus on this one. An executor service is handling several threads, regular threads. We're going to call them platform threads. because they are really wrappers on the kernel threads. And this fixed pool of threads is accepting tasks, and the tasks are stored in a single queue attached to this executor service, and all the available threads are going to take a task from this queue to execute it. So in an executor service, you have one single queue for all the threads that you can have in it. Okay? And then 10 more years are passing, up to 2014. That's Java 8, for the few of you who are still working on it. And there are two main things that have been added to the JDK in the concurrent space. The first one is the fork join pool and the fork join framework. Maybe some of you have played with the fork join framework? Yeah? Oh, yes, several people. Do you like it? Who likes it? Ah, 1%. That's probably 10% of the people who really liked it. It's a little technical, right? It's not that easy to set up things properly. The fork join pool is used in parallel streams. Now, maybe you've been playing with parallel streams. The nice thing is that this fork join pool becomes completely transparent. You just call parallel on your stream, and it will be executed in parallel on this fork join pool. Now, fork join pool is also a pool of threads. The big difference between the executor service and the fork join pool is that you have only one waitlist in an executor service, where you have one waitlist per thread in a fork join pool. And this has been done in that way due to the way this fork join pool is working. Actually, the idea is to have one task that is going to be split into at least two tasks. And these two tasks are going to be added to the queue of this thread. But fork join pool also implements work stealing. Okay, so if the thread is doing nothing, whereas another thread is busy and has a queue that is full, then the other thread that are doing nothing can steal tasks from the waitlist of this thread. This is how the fork join pool is working in a nutshell. And the other thing that has been added in 2014 as part of the Java 8 is the completable future API. Okay, and completable future is an attempt to have an asynchronous programming model within the JDK. Okay, maybe some of you have been playing with the completable future API. Oh yes, that's a lot of people. Do you like it? That's a little less people, but still a fair amount of you. Great, okay. So the good news is that you will not have to play with computable futures anymore. And yes, that's a good news. Okay, so you can see that every 10 years, something new is happening in the concurrent programming space in the JDK. And guess what? We are 10 years after 2014, almost. So Loom is coming. That's 10 years after the last update of the programming, of the concurrent programming model. Among all this stuff, there is one thing that stays the same, that didn't change, is that once you have submitted a task to a thread, you cannot detach this task from this thread anymore. You cannot do that. Okay? Either this task is going to produce a result, or an exception, or you kill the thread, you interrupt it. And that's it. Okay? So you have a problem there, because if this task is actually buggy and blocking this thread, then you're doomed, because you have a platform thread that is doing nothing, and there's nothing you can do with it, apart from killing it, which is quite annoying. And that's why people have been doing asynchronous programming, actually. Okay? Now we are in 2023. We'll soon be in 2024, by next year, I would say. Okay? And we already have almost all of Loom as a preview or incubator features, and in September, we will have part of it as a final feature. What is Loom about? Okay? And to understand that, you need to ask yourself the question, why are we writing concurrent code? And if you don't have any answer to that question, stop writing concurrent code. Because it's hard. When you have bugs, they are hard to fix. Okay? If you've ever fixed one race conditions in your life, you know that how hard it is to fix this kind of bugs, because you can't really reproduce that on your machine. It's super hard to reproduce. Okay? So you need to just analyze your code with your own eyes and try to understand that and make sure that you know your concurrent courses super well to fix that. There are actually two contexts where you can use concurrency. The first one is basically the parallel stream concept. So you have a massive computation to conduct, like a big array to process, and you're going to split this array into as many cores as you have, split the computation on all the cores of your CPU. That's basically what parallel streams are doing, and then gather all the partial results into one result, and that's it. Okay? This is in-memory computation, non-blocking computation, and this is not what Loom is about. If you're doing this kind of concurrent programming, don't touch it. Don't try to run it on virtual threads. This will probably be actually slower to run parallel streams on top of virtual threads than on top of platform threads. Okay? This is not the use case for Loom. The use case for Loom is about I/O and blocking operations. Okay? You have requests to make on server requests, database, anything going through the network. This is blocking, and we're going to see more about that in a minute. This is blocking. If you have a blocking code, then running on top of virtual thread will bring you amazing performances. That's the most important thing to get out of Loom. Okay? Loom does not accelerate your in-memory computations. Let me say that again. Loom does not accelerate your in-memory computations. It will probably slow them, so don't do that. What is happening when you're doing I/O in your application? Suppose you have some code that is querying some kind of server over the internet. Okay? The first thing you need to do is to prepare your HTTP request, right? And this is basically about processing strings of characters. This is in-memory computation, and nowadays the CPUs are running that in the order of nanoseconds. Let us say like 10 nanoseconds. Okay? And then when your HTTP request is ready, you just use your HTTP client to launch it on your network, on the internet, and then the time scale becomes the millisecond, because going through the network is in the order of the milliseconds. All right? And then you get your response. There's a JSON object in it. You need to transform this JSON object into your Java object. Could be in any other language, by the way. This is not depending on Java, right? It's the same for every language. And then it's in the order of the nanosecond again. So basically you end up with this kind of stuff. You have a thread that is working nanoseconds to prepare a request. Then we launch the request on the internet and wait for the result. That's milliseconds. And then we spend nanoseconds to process the response and give the response back as Java objects for your application. Okay? So the thread that is running that is actually doing nothing on an average, because there is a factor of 1 million between milliseconds and nanoseconds. If you want to draw this sketch at the right scale, I suppose if you have 1,000 pixels, it's probably 2,000 actually, in the width of the screen. Well, then the red part will be 2,000 pixels, and the green part will be 1,000th of a pixel, so you won't see it. That's the right scale. Okay? That's the right scale. How many threads do you need to keep your CPU busy? Well, that's quite easy to say. You need 1 million threads. Have you ever tried to launch 1 million threads on your machine? Yeah, it doesn't work very well, yes? How many threads can you launch on a machine? 2,000? 3,000? 4,000? 5,000? Yeah, that's probably the maximum you can do. Not more. Why? Because the thread actually is not cheap. The thread in Java, the thread class that has been there for 25 years, as I just showed you, is actually a wrapper on a kernel thread. Launching a kernel thread takes in the order of millisecond, and it will allocate 2 megabytes of stack upfront to work. So if you want to launch 1 million threads on a machine, on any machine, and this is OS dependent, it's not really Java actually. Okay, so if you want to launch 1 million threads on a machine, it will take you about 20 minutes, if it works, and you will need something like 2 terabytes of memory. I don't have 2 terabytes of memory on this laptop, so I can't show it to you. But if you have that, well, you can try and see if it works. Okay, so it's basically not working. If you want to scale an application and keep your CPU busy, CPU that you bought that is so expensive, You need a million thread, and you can't have a million thread. So you need to find another model. And this other model that has been working for 10 years now, which is it's kind of great, but also has drawbacks, is going asynchronous. Asynchronous is about saying, okay, I can't have as many threads that I need, so I need to find another model for my tasks. I need to find a model of tasks that is not blocking my virtual thread, my platform thread. Because if I'm blocking my platform thread, then I need another one for the next task. And I can only have several hundreds or several thousand of such platform threads. So I can't do that. All right? And that's all the frameworks that are doing that build on top of this paradigm concept, well, programming concept, which is asynchronous programming. Asynchronous programming leads to code that is probably hard to write, I would say. Even harder to read, because, and we're going to see examples of that. If you don't believe me, just, if you don't know what callback hell mean, just type in that in your favorite search engine and you will have an idea of what it is. It's also hard to unit test, because you can't really unit test it, actually. You can unit test the tasks, but unit testing how these tasks are wired together is next to impossible, and it's hard to debug, of course, and also impossible to profile, because what you're really profiling is actually your framework. It's not your application. Yes, typical profile. That's the blocking code. Okay, you get your request as a JSON object or whatever. You send this request on the web. That's your blocking code, actually. You unmarshal this JSON object to get your contract object. This is the object you want to get from your REST service. This blocking code is actually simple to understand. It's just basic imperative code with method calls and this kind of thing. And that's the non-blocking version. Okay, completable future, that async, you pass this supplier or function or whatever, and then apply. Exceptionally, that's what you do to handle your exceptions, and then apply to unmarshal your result. The problem is that if you put a breakpoint in this code, the breakpoint will not show you the right stack. It will show you the stack of your framework, actually. But you don't know that when you're calling do something with the exception, for instance, you did this build contract, because it's not in the stack anymore. It's gone. It has been executed already. Okay, and if this code is buggy, if you have a task that is actually blocking, because your code is not blocking, it's super hard to find in your application, because it's not blocking anything. Okay, when you have a thread that is blocked, you can query your JVM, hey, show me the threads that are actually blocked, and then you'll be able to debug that. But in that model, it's not the case anymore. So good luck debugging that. So that's the first solution. Change the model of task. Instead of having one big task, imperative task, that's the first code. Split it into several subtasks that are non-blocking, and push this non-blocking task into some kind of framework that will chain them in a non-blocking way. Okay, that's the first solution. But there's another solution, which is changing the model of thread. Okay, if you can create threads that are easier to launch, cheaper to block, and cheaper to kill, then you're good. You could keep the first version of this code. Now, what is the factor you need to gain performance-wise on this thread optimization? Well, it's a factor 1,000. That's a lot. You need to have threads that will consume the thousands of the memory that is consumed by a platform thread, and that you can launch in the order of microseconds instead of milliseconds. That's basically the goal. And guess what? This is what virtual threads are actually doing. Okay, so the other solution is cheaper thread by a factor of 1,000. A Loom virtual thread is about 1,000 times cheaper than 1,000 thread. So actually launching 1,000,000 thread, even on this kind of laptop, is okay. It's perfectly okay. It's fine. The memory consumption is in the order of the kilobytes. So there's a factor 1,000 there, and it's going to be optimized in the next version, in the upcoming versions of virtual thread. The API is stable, and the language modifications are stable, so that's okay. It can be published now, but it will still be optimized in the future. And the creation time is indeed in the order of the microseconds. So a virtual thread is not free stuff, but it's much cheaper than platform threads. So you can have basically as many virtual threads as you need. No problem with that. First consequence, why would you pull virtual threads? Why would you pull a resource that is cheap to create, cheap to block, and also cheap to let die? Because if it's cheap to create, then you can let it die and create another one. There's no problem with that. And that is going actually to solve also many other problems with that platform threads have, and we're going to see them later. So how can you create a virtual thread? The thread class has been modified so that you can create thread actually with factory methods. Back in the day, you would do new thread something, and actually you shouldn't be doing that anymore because now you have this executor service pattern that is the preferred pattern to actually create platform threads. Okay, it's much better to do that than doing new threads and start. But with virtual thread, it's okay. You can create them with off-virtual. You also have an off-platform factory method that will give you a different instance of thread. And you can either start them passing your runnable as an argument, or you also have an unstarted version, and then you call start later on this virtual thread. You can do both. Okay? So if you want to play with virtual thread, it's as simple as just writing this code and calling it. Now you also have an executor service that is not, well, executor service are pool of threads, but actually this executor service is not a pool of thread because it's empty. It's just creating a virtual thread on demand when you're submitting tasks to it. So if you submit and provide a a runnable or a callable, it will just create a virtual thread and let it die in the end. It doesn't pull anything. So if you're having a concurrent application and you want to test performances with virtual threads, and you're built on top of an executor service, you can just try this executor service, and it should work out of the box. Now, the virtual thread that the object you get when you call this factory method is actually an instance of a class that is not public, so you cannot access it directly, which is called virtual thread. And this virtual thread class is an extension of the thread class. So a virtual thread is actually a regular thread, does not work the same, but as far as all concurrency, visibility, race conditions, etc., all this good stuff from a concurrent programming is concerned, then virtual threads work the same with platform threads. Okay? So that's good news. All the bugs you had with platform threads, you still have them with virtual threads. Sorry about that. What is the price of blocking a virtual thread? Because all this non-blocking stuff is about avoiding blocking a platform thread, because if you block a platform thread, then you need to create another one, and this is expensive. So this also has been fixed, and blocking a virtual thread is actually super cheap, and I'm going to show you why. In memory, you have this heap memory, which is the piece of memory in the Java application where you create basically all your objects. And a virtual thread is something that is going to be executed within a fork join pool. Now, not the common fork join pool, another fork join pool that is launched for you when the JVM starts. So that's another pool of thread that you have. And this fork join pool is going to create a certain amount of platform threads. By default, the same amount as the number of cores your CPU has, or almost the same amount. And when you launch a virtual thread, this virtual thread will actually be mounted on top of one of the platform threads of this fork join pool. So a virtual thread is actually wrapping your task, runnable or callable, and is mounted on top of what is called a carrier thread, and this carrier thread is actually a platform thread from this fork join pool. Okay? And the object that is taking care of that is a continuation object. Now, this continuation object is not a public object. It's hidden in JDK, internal VM stuff. I'm going to show you that in a minute. So you shouldn't try to play with continuation. Actually, you can't. Well, actually, you can, but you can't. And certainly don't build your application by using this object. Don't do that. Okay? And what is happening when this thread is blocking, for instance, on some I/O? Well, the continuation will detect that, and we'll call this magic method called yield. And continuation.yield will actually unmount these virtuous threads from this carrier thread. So the virtuous thread is blocked. If you keep it on this platform thread, it will also block the platform thread, but precisely you want to avoid that, and this continuation object is there to avoid this situation. So it will just move the stack of this virtuous thread from the stack of this platform thread to the heap. Okay? And now the portion of code that is blocked is actually kind of backed up in a heap, and the platform thread you had is not blocked anymore and is available to run another virtual thread. So you see that the previous situation where giving a task to a platform thread was you were in a situation where you could not detach this task from your platform thread. Now you can do that with this virtual thread, which is some kind of wrapper around your task. And this wrapper, you can unmount it from the platform thread. Okay? Java is the only language that is able to do that in that way. There's only one also that is doing that, which is Haskell. Erlang. Maybe some of you have worked with Erlang already? No? Yeah, several people. So that's actually what Erlang was doing years ago. That has been recreated in the Java platform. By the way, it also means that all the garbage collectors that are working with the different stacks of the different threads had to be updated, because now they need to look for the portion of stacks that are in the heap. Okay? 100,000 lines of code. Yes, there are updates of all the garbage collectors of the Java virtual machine to handle that. All right, and so at some point, the OS will signal, hey, the data is ready. You can have it, and you're not blocked anymore. So the continuation has a handler that is listening to this signal, and will signal that, and will just call a run method, and this run method will take this portion of stack from the heap memory back to the stack of this platform thread. Okay, and the platform thread will continue running this virtual thread. But remember what I just told you is that a function pool has actually as many waitlists as there are threads. So this diagram is actually a simplification. This portion of the stack is actually put as a task in this waitlist. And if the platform thread 1 is busy and platform thread 2 is actually not busy, then it will be able to steal this task from the other waitlist, because this is what function pool does. Okay, move it to the other platform thread, and you will end up in this situation. So actually, your virtual thread, if you block it, run it, block it, run it, block it, run it, because this is how you should write your code, then you will see that it will jump from one platform thread to the other in the meantime, and that's okay. That's perfectly fine. This is how it's working. Okay, so the cost of blocking a task is actually the cost of moving, let's say, 10 kilobytes or 100 kilobytes of memory back and forth from the stack to the heap, and back from the stack to the heap. That's the cost. So it's not free. Nothing is ever free, but it's much cheaper than blocking a platform thread and having to create another one, which may even be not possible. Okay? So blocking a virtual thread does not block your carrier thread. It's not blocking your platform thread anymore. So if you write blocking code and you're running on top of virtual thread, your code will be blocking, that's fine. Your virtual threads are going to block, that's fine too, but your platform threads are not going to block. And this is what you want. So that's really a new way of seeing blocking code. Writing blocking code is actually now okay. You don't need to think about super complex system to avoid writing blocking code. So why would you write non-blocking code? Do you prefer to write the first version of the code or the second version? Okay, it's up to you. It's really up to you. I would like just to show you some demo, because I have a demo that is ready there. Okay, let me do this in that way. just to show you how it's working, and it's working in a super simple way actually. Okay, so this is a Spring Boot application. Okay, I'm just you can this is Spring Boot 3. It's not the very last version of Spring Boot 3, but a recent version, I would say. And you know that in Spring Boot you can actually decide which executor service is going to handle your HTTP request. Okay, so it's this piece of code here, this Tomcat protocol handler customizer, and you can set this the executor with the executor service I just showed you, which is the executor service that actually creates virtual threads on demand. So if I just commented this stuff, so I'm going to run you to create this, to launch this Spring Boot app. I'm using the JDK 20, so it's the last version actually. Okay, I'm going to go to my browser. There, great. And this page is a wonderful page. I'm a real expert in CSS, as you can see. Oh, you're laughing. This is not kind. And here I have a service that is just displaying the name of the thread that is executing this task. And you see that that's actually a regular platform thread. Okay? And you can see that I'm running 3, 7, 6, and you see that the number of threads is actually looping in a closed set, because in this executor I have only a limited number of platform threads, and I'm using one after the other. Okay, this is not a very loaded server. There's only one request every minute, so that's okay. Probably your application is doing more than that. But oops, oh no, come on. So doing that again. So that's the way it's working with virtual. The second thing I would like to show you is what's happening when you throw an exception. So this service is just throwing a null pointer exception. Okay, so you have this. So null pointer exception is there. All right, this is my code. Paumard.loom, travel page, well, it doesn't matter. Okay, all this is the Spring Boot application up to here, and at the very bottom of it, I have this thread.run because I'm running in a platform thread. All right. Now, if I'm switching to virtual threads, I'm going to stop you, uncomment this declaration here. Okay, so now the executor service that Spring Boot is going to use is the one that is creating one virtual thread per HTTP request. So let me launch that again. Okay. Go back to this wonderful application. Now we're going to see the current thread. And you see that the current thread is now virtual thread 216 running on top of this carrier thread, which is taken from this fork join pool 1, and the name of this thread is worker1. Okay, that's the carrier thread that is actually running this virtual thread. And if I refresh that, you will see that the number of this virtual thread keeps increasing. Okay, it never decreases. Why? Because this executor service is just creating a new virtual thread and just let it die, and that's okay. And if I show you the exception, okay, so that's still my null pointer exception in the exact same service, of course. And you see that the stack trace is actually exactly the same. There's no difference. Okay, the only difference is here. It's just there. Well, actually there. And you see that at the bottom of it, you have this continuation.enter object that is actually executing this virtual thread. And you cannot see the platform thread underneath. The platform thread is actually hidden from this stuff. Please, can you come back? Oh, come on. Oh, shit. Anybody who was here yesterday? Yeah, okay. I'm sorry. All right, so you see that embracing virtual thread is actually super simple. If you have an application and you want to test it with virtual thread, it's really super simple to try. Come on. Oh, gosh. All right, let me go back to the slides. I'm going to exit this presentation mode, go back to this stuff, and carry on with the presentation. I hope that, yeah. So now you have plenty of threads. You have millions of them, literally, okay? And you know that, I don't know if you're using what IDEO you're using, but when you're debugging, you have this small window that shows you all the threads of your application, okay? And if usually you have maybe less than 100 in it, now you can have 1 million of them. Actually, I never tried, but is this small window going to be able to handle 1 million threads in it? I'm not so sure. But if you want to debug something in it, and you want to find the thread that is running the code that you want to debug, maybe the wheel of your mouse will die before you find it, actually, because you have 1 million to scroll through. So you need to do something about that. Okay, having actually 1 million threads, you need new tools to handle them. The executor service is not the right model anymore. And this is why people have been developing what is called structured concurrency. Okay, structured concurrency is about arranging all your threads in some kind of structured stuff, just as you create directory to handle millions of files on your hard drive. If you have only 5 files on your hard drive, it's okay, you don't need directory. You don't need folders. But if you have 1 million of them, then you definitely need folders because you're not going to be able to find them anymore. Okay? So the main object of structured concurrency is an object called structured task scope. All right? And it acts kind of in the same way as an executor service. You submit tasks to it, it creates a virtual thread to execute this task, and then you call join on this object. It's going to tell you all the tasks you've been submitting either have produced a result or through an exception. So you're done. And then you can analyze your result. So I'm going to show you an example, super simple. You want to build a travel page, and there are two information on this travel page. That's for travel agency. The price of the travel you want to buy, and the weather forecast. Weather forecast is nice to have. Quotation is probably important because if you want your customer to pay for something, you probably need to show a price, right? If you want to implement this simple problem with asynchronous code, you'll end up writing this kind of code with the completable future API. Is it simple code? Well, it's probably not that hard to write. It's probably a little harder to read, but it has all the drawback of asynchronous code. All right. Actually, I think that the biggest problem with this code is that when you're looking at any kind of task, you have no clue, and the information is actually not there, what thread is executing what task. This information is not there, and you can't know that. You need to have the context to know that. And actually, this problem is a big simplification of the real problem you want to solve. Because the real problem you want to solve is this one. You want to query several quotation servers and get the best price. And on the other hand, for the weather forecast, you want to query several weather forecast servers and get the first that is going to answer, because all weather forecasts should be the same. Okay, it's just like querying a DNS, for instance, domain name server. So the pattern of code you will end up writing is this one. You create your weather scope object, and I'm going to give you hints about doing that. That's an extension of structured task scope. Okay, you fork your task, query first server, query second server, query third server. You call join, and then you analyze your result. Okay, so you have just a few methods to write, but they are all business methods. This is purely imperative code, mono-thread, no multiple thread there. Your tasks are going to be executed, every task is going to be executed in its own virtual thread, and that's it. Much simpler code than the completable future pattern. And it's the same for quotation scope. Quotation scope is exactly the same code. Just write the same code, and that's it. And it's going to be the same for the travel page scope also. Just write the same code. Using a structured task scope is always the same pattern, which makes your code much less error-prone, actually. Okay? So the only complex method that you need to implement in this structured task scope extension that you're writing, because this travel page scope object is actually an extension of the structured task scope class, is this one, handle complete. It's a callback on a future. Every fork is actually returning a future, but you don't need it in your business code. You need it internally. And you have 4 states for this future. Running, which should never happen. Success, I have a result. So I'm going to store these results in some kind of collection. This collection has to be thread safe, of course, because all these calls are happening in a virtual thread that is actually executing your task. And failed means that there was an exception and you need to store it also somewhere. And cancel is something else. And once you have that, for the base quotation, for instance, computing the base quotation is just about getting the mean according to a certain key, which is the price. All right? And this is purely imperative, super simple code. This is Java 8 code, by the way, code that you could write already 10 years ago. And the same for exceptions. And this code is super simple to unit test. If you want to unit test this kind of method, it's really a no-brainer. Okay? So Loom is giving us 3 structured task scope objects in the current incubator version of structured concurrency. The first one is just fork your tasks, join to make sure that all the tasks are done, and get the results through the futures. You could get them directly in your structured task scope or in the extensions. There's a second one which is called shutdown on success. And the semantic is that the first task that will produce a result will shut down the scope and will produce that result. So all the results should be equivalent. And you're okay to get the first one. That's for DNSs or weather forecasts. And the last one is shutdown on failure. And shutdown on failure will fail, the scope itself will fail as soon as one of the tasks is failing, not waiting for the other. So if you have like 50 tasks and the first one is already failing, then all the others will be cancelled, because the semantic of this task scope object is that you cannot produce a result if one task is failing. Okay. The last thing is I would like to talk to you about is scope values. And scope values is about replacing, well, not really replacing, but providing another way of having ThreadLocal variables. ThreadLocal variables are for threads. It's important to have them because sometimes you want to pass information to a certain portion of your application, but you don't want to pass them through third-party dependencies because first you can't, and second, if it's secret information, you want to hide it from these third-party dependencies. So that's important to have them. Okay. But it's not the best model to work with virtual threads. Now, the good news is that ThreadLocal variables are fully supported by virtual threads. So if your application is using them, you can still run on virtual thread and that will be okay. It will work, but you can do much better with precisely scope values. The biggest difference with scope values is that scope values are immutable, whereas ThreadLocal variables are actually mutable. And that's a problem because it means that the JVM cannot really optimize them because it has to keep them in one place and everybody should be pointing to the same place. Whereas when it's really a value, it can inline them wherever it needs, which is better. And the second biggest difference is that the scope value is not bound to a particular thread, which is a good news because you are going to launch so many virtual threads in your application that you don't want that. Okay? This is the main pattern of code that you're going to use with scope values. You create a scope value object with this factory method, and then you have a runnable, which is your task. And you need, if you want to use this scope value, you need actually to bind the value to this scope value and make this binding available in the context of the execution of your task. So here I have 4 contexts to run this task. First, task.run. No binding to the scope value. So the scope value is not bound. So here you will have unbound if you run this code. The second one is the second line of code where key is bound to key 1, and then you run your task. And if you run that within this task, you will see that the license key is actually bound to the value key 1. Okay? And if you run the third line where key is bound to key 2, and you run your task again, it's always the same task, but this time this task will see that the license key is bound to the value key 2, and if you run it a fourth time, now the key is not bound in the context of this task, and so you won't have any value. Okay? So you can see, and everything is happening in the same thread here. I didn't launch any virtual thread or any platform thread. So scope value is really about setting a value in the context of the execution of a task, which can be a runnable or a callable, whatever the thread you're executing this task in. Okay? So scope value are bound to the context of calling this task. they are not transmitted. If this task is launching virtual threads or platform threads by hand using the factory method I showed you, then the scope values are not transmitted to these virtual threads or platform threads. But if you're launching structured task scopes, and this is what you should be doing, really, then the bindings are transmitted to the thread created by these task scopes. That's the biggest difference. And this is a good thing, because an executor service is actually attached to the life cycle of your application. You create it when you create your application, and it's all there until the end of your application. Whereas the structured task scope is just bound to a set of requests you're doing. It's a much short-living object, which is better. So what are the plans for the current JDK 21? As of now, all this is preview or incubator. In 21, virtual thread should be final. They are already merged in the main branch of the JDK 21. Concurrency and scope value should be preview features, and we'll probably make it as final feature in the future, probably 22 or 23. And this is what I wanted to talk to you about Loom. I'm sorry we are up. Time is up, so I don't have the time for questions. But if you have questions, please reach out to me, and we can discuss further about these things. Thank you very much.